Hi, I'm Isaac. I'm a postdoc at the Max Planck Institute for Software Systems, and I'm here to talk about heterogeneous Paxos, which is a project I worked on mostly at Cornell with Xinwen, Wang, Robbert, Renesse, and Andrew Myers. Most of you know that consensus is a key part of maintaining a replicated database, blockchain, anything else with consistent state. A consensus protocol is the part that decides which transaction goes next. Traditional consensus algorithms are built for traditional scenarios, usually one system owner running a few machines, trying to tolerate one or a small number of independent failures. Crucially, most distributed algorithms are what we call homogeneous, as opposed to heterogeneous. And by that I mean three things. First of all, that all participants are created equal. There might be different sets of participants with different roles, but within each role, any participant is just as good as the next. Usually, a system is characterized by having some number n participants. Secondly, all failures are created equal. Usually, when we're analyzing a system, we talk about tolerating some number f independent failures, all of one type, so f crash failures or f Byzantine failures. Third, all learners are created equal. Learners are the people who observe the output of the consensus. They make assumptions about which failures need to be tolerated and which results need to be guaranteed. Traditionally, these assumptions are something like, there must be at most f failures out of the n participants. Previous projects have managed to break each of these assumptions independently. Upright and XFT, for example, mix crash and Byzantine failures. Byzantine quorum systems and refined quorum systems use quorums to encode heterogeneous participants. Ripple was a consensus protocol designed with heterogeneous learners. Even pairs of homogeneous assumptions have been broken. Stellar has heterogeneous learners and participants. Flexible BFT has heterogeneous failures and learners. And I'm here to argue that not only could Byzantized Paxos be phrased with heterogeneous failures and participants, but we can adapt it to form a new protocol, Heterogeneous Paxos, which is heterogeneous in all three ways. And I think that's really important because a lot of new systems, including most permissioned blockchains, are trying to connect lots of very different people with very different assumptions. For example, in 2016, all of these companies were trying to run a blockchain together with R3. And of course, the actual machines running the consensus are different too. All of these companies, for instance, can be used to run consensus participants in addition to servers owned by stakeholders in whatever system you have. People are going to have different opinions about the trustworthiness of participants in each of these services. And not all failures are independent. Machines sharing an implementation are more likely to be hacked and go Byzantine together. Machines that are in the same data center or the same power grid are more likely to crash together. Machines owned by the same people are more likely to fail together. Correlated failures happen all the time, so it's not always accurate to tolerate any F independent failures. To build a system that works with many different parties, we should use a consensus that takes everyone's specific failure tolerances into account. For our project, we're working with some fairly standard distributed systems assumptions. And we want our distributed system to keep working even when some participants fail. Crash failures are when a node simply stops functioning without warning, without detectability. Byzantine failures can behave however they want. They can send messages that aren't part of the protocol, send messages out of order, they are arbitrarily evil. There's one other critical component of distributed systems. Someone observes the output of the distributed system. Someone makes these demands about failure tolerances. And in consensus, we call that entity a learner. Usually we think of learners as people interested in results of the system. In a consensus problem, we have some known participants who for historical reasons are called acceptors. And there are also some learners. And each learner wants to decide or learn a value, such as what transaction happens next. The key property of consensus is agreement. We want learners to decide on the same value. And we want this even in the presence of failures, either acceptors crashing or becoming Byzantine. The most famous consensus algorithm is Paxos by Leslie Lamport. The original Paxos tolerates only crash failures, but there are several variants designed to deal with Byzantine failures as well. The most famous of these is arguably practical Byzantine fault tolerance, but our protocol builds on Lamport's Byzantizing Paxos by refinement, mostly because it's easier to prove stuff about. We usually think of Paxos as a homogeneous algorithm. As a reminder, that means all acceptors are created equal, all failures are created equal, and all learners are created equal. But I'm here to tell you that we don't always want to operate under homogeneous assumptions. Sometimes we want heterogeneous systems. These are systems where many different, not necessarily symmetric, tolerated failure conditions, where there can be some crash failures and some Byzantine failures tolerated at the same time, and where different learners make different assumptions about what may happen and what guarantees they want under which conditions. Heterogeneity means that we can tailor the system to the specific constraints of the learners and the potential failures of the acceptors. In the case where everybody is really the same, we want our heterogeneous system to reduce to the homogeneous version, but otherwise we should be able to tolerate more failures, be more efficient with our resources. Okay, so what does it take to have a heterogeneous consensus algorithm? Well, it has to be heterogeneous. That means many different failure scenarios, mixed Byzantine and crash failures, different learners make different assumptions. And it has to be consensus. Formally, it needs three properties: non-triviality, agreement, and termination. Let's take a closer look at what these consensus properties mean in a heterogeneous setting. Non-triviality requires that if a learner decides something, that thing must have been proposed by someone who's allowed to propose it. You can't always decide 3 because 3 may not have been proposed. It doesn't matter whether you're in a homogeneous or heterogeneous setting. What we're going to do is have our learners check that a value was signed by an authorized party before they decide it. Done. Agreement is trickier. If 2 learners decide, they decide the same thing as long as failure assumptions are met. In the homogeneous case, this is clear. Either there were too many failures or there weren't. In the heterogeneous case, not so much. Whose failure assumptions are we talking about? Who should agree under which assumptions? And termination is tricky too. Obviously, each observer can't decide if, say, all the participants fail. In the homogeneous case, if there aren't too many failures, we want all the learners to decide, but we haven't yet defined aren't too many failures in the heterogeneous case.
Alert! It is technically impossible to guarantee non-triviality, agreement, and termination even in the homogeneous setting if you want to tolerate failures and make all the assumptions we've made so far. Protocols get around this by either using randomness cleverly, in which case they may show probabilistic termination, or by guaranteeing termination only when there exists some unknown time after which there exists some unknown message latency bound. Paxos uses this weakened partially synchronous termination property, and it's what we use as well.
Anyway, we're left with 2 questions. How do we express heterogeneous failure assumptions as opposed to homogeneous ones? And can we make a consensus algorithm that works under those assumptions? But before we can answer those, we have to go back and learn a little more about Lamport's Paxos. Everyone remembers Lamport's Paxos as the optimal homogeneous consensus protocol. That means, among other things, that it can tolerate strictly less than half of the acceptors crashing, or a different version can tolerate strictly less than a third of the acceptors being Byzantine. But it's usually set up exactly like that. Tolerate F out of n Byzantine failures, or tolerate F out of n crash failures. Pretty much every implementation I've come across does it this way. But Paxos can easily be defined in a much more general way, in terms of quorums, which are subsets of participants. When your quorums are just any n minus f acceptors are a quorum, it has homogeneous properties. But the actual requirements are more general. Intuitively, a quorum is a subset of acceptors which is sufficient to make a learner decide. For a system to have termination, at least one quorum must survive, and for a system to have agreement, you can't have 2 quorums with an intersection that is entirely Byzantine. So, if there are some crash failures, but a quorum survives composed of non-crashed participants, they can allow a learner to decide. But if there are two quorums whose intersection is wholly Byzantine, then each Byzantine acceptor can bisimulate, meaning they act one way for the purposes of one learner and act another way for the purposes of another learner. And that means that each quorum can make a learner decide, and they don't necessarily decide the same thing. We don't have agreement. If there are safe acceptors in the quorum intersection, that can't happen. The safe acceptor won't bisimulate. Now, it so happens that with 6 acceptors, you can make a Paxos where any 4 are a quorum. And this Paxos will tolerate 1 Byzantine and an additional crash failure, but not 2 Byzantine failures. So this quorum-based definition is already a little bit heterogeneous. So, returning to our questions, how do we express heterogeneous failure assumptions? Well, with the quorum-based Paxos, they're embedded somewhere in the definition of those quorums. And can we make a consensus algorithm that works? Well, Paxos already kind of is for 2 out of 3 kinds of heterogeneity. Specifically, not all acceptors are created equal and not all failures are created equal. But what we really want is to be able to express our learners' assumptions in advance and then see if we can get a consensus protocol from them. So we're going to do it using a thing we call a learner graph. On the learner graph, the nodes are learners. We'll label each learner with the conditions under which it demands termination. And each edge is labeled with the conditions under which that pair of learners wish to agree. So, suppose we have a pair of learners, I'll call them red, and 5 acceptors. Red learners want to terminate even if 1 acceptor fails. But they also want to agree even when 1 acceptor is Byzantine. In practice, a traditional consensus tolerating 1 Byzantine failure will work for them. But suppose that there are 2 more learners who I'll call yellow, and yellow learners want to terminate even when there are 2 crash failures. But yellow learners accept that they may disagree if there are any Byzantine failures. I'm labeling the edge between them blank to represent no Byzantine failures. This is simple enough if red and yellow learners don't want to agree. Red learners run a 1 Byzantine tolerant consensus, and yellow learners run an entirely separate 2 crash tolerant consensus. But what if the bottom yellow and red learners also want to agree? At least when there are no failures. In fact, agreement is transitive. When there are no failures, the bottom 2 learners agree, and the red learners agree, so the top red learner agrees with the bottom yellow learner. And for this graph, the red-yellow pairs will in fact have to agree when there are no failures. Now, there is a consensus that can satisfy this observer graph, but first I want to explain exactly how we implement these labels. Edge labels express when 2 learners want to agree. If we're worried specifically about Byzantine and crash failures, then it turns out that what we really have to express here are which acceptors are safe. That is to say, which acceptors won't send wrong or out of order messages. Even a crashed acceptor is safe, but a Byzantine acceptor is not. So, if we want to tolerate any 1 Byzantine failure out of 5 acceptors, then any 4 acceptors are a safe set. The learners demand agreement whenever the elements of 1 safe set on the edge label are non-Byzantine. I've only drawn 1 safe set here, but this label actually should have 5 safe sets, 1 for each possible tolerated failure. When we're only considering Byzantine and crash failures, it turns out that the conditions that matter to a learner for whether it can terminate concern who can crash. Usually we assume that Byzantine nodes can crash, but you can represent alive but corrupt failure types. So, if yellow learners want to terminate when any 2 out of 5 acceptors have crashed, then they must terminate with any 3 live acceptors. By tradition, these live sets are called quorums. They are sets of acceptors necessary to make a learner decide. So on our learner graph, red learners have a quorum of any 4 acceptors, and all edges with the yellow learner have one safe set consisting of all the acceptors. So now we're ready to build a consensus for these learners. But first, we have to take one more look at Lamport Paxos. Paxos involves a step called 1b, in which acceptors respond to the question, is there any reason we can't consent on this value? And one possible reason is, I've previously accepted something else. Now, I should note that accept is a thing that acceptors do in Paxos. It is not the same as when learners decide. However, this is the step that ensures that intersecting quorums can't make learners decide different things. The acceptors in the intersection will have a reason to put in their 1b's. So, we're going to make two changes to Byzantine Pax. First, we're going to run a different instance of Paxos for each learner concurrently. So, if we're talking about these two learners, we run two different Paxoses, one red, where any 4 acceptors are a quorum, and one yellow, where any 3 acceptors are a quorum. And second, in these Paxoses, 1b's can include, I've previously accepted something else in another Paxos. That prevents the two learners from deciding different things under some conditions. Now I know what you're thinking. Isaac, that sounds terribly inefficient. You're running a different Paxos for every single observer. Well, in reality, the vast majority of conceptual messages for each conceptual Paxos share an instantiation on the wire with messages from other Paxoses. Most notably, if learners' connections all have the same label, we're exactly the same as regular Paxos. For this graph, the Paxoses for the red learners have quorums of any 4 acceptors, and for the yellow learners, any 3 acceptors. So long as there is at most one crash failure, there will be one live red and one live yellow quorum, and they all intersect. If there's a Byzantine failure, red learners will agree, but yellow learners may not. And if there are 2 crashes, the yellow learners will agree and terminate, but the red learners may never terminate. So at last we have a consensus with that third kind of heterogeneity. Not all learners are created equal. So returning to our questions, how do we express heterogeneous failure assumptions? With a learner graph. Each learner expresses their termination conditions, and each pair expresses their agreement conditions. Can we make a consensus algorithm that works for them? Well, clearly sometimes yes, because we just did one, and sometimes no. If 2 learners want to agree even when all the acceptors have failed, that's not possible. We need to generalize Paxos's quorum requirements. Recall that Paxos requires that 1 quorum survives, and no 2 quorums intersection is entirely Byzantine. And this is what our generalization looks like. To summarize, under the conditions of some edge of the learner graph, any quorum of one learner must have a non-Byzantine intersection with any quorum of another learner. In order to guarantee termination, just like in the homogeneous case, a learner must have a live quorum. So yes, we know exactly when we can make a consensus algorithm that works with the given graph. We run our transitivity process to condense the graph, and then we check if heterogeneous consensus is possible. We've implemented heterogeneous Paxos, mostly to show that we can, and also to show that there are performance benefits from heterogeneity. We used the Charlotte framework for authenticated distributed data structures to build blockchains where each block requires a proof of consensus referencing another to prove that the reference block belongs in the chain. This was implemented in about 1,700 lines of Java with fairly standard building blocks. So for one experiment, we have an organization we call Red. Red has 2 learners and 3 acceptors. And red learners want to terminate even if an acceptor has crashed. But they accept that they may not agree if an acceptor is Byzantine. There is also another organization we call Blue. Blue also has 2 learners and 3 acceptors. And red learners do not care about blue acceptors. Red learners want to terminate even with all the blue acceptors crashed, and red learners want to agree even with all the blue acceptors Byzantine. And blue learners, likewise, don't care about red acceptors. They want to terminate even when all the red acceptors have crashed, and at most 1 blue acceptor has crashed. And they want to agree as long as none of the blue acceptors are Byzantine, regardless of the behavior of the red acceptors. Now I can tell you right now that no consensus is going to use only these participants and get the red and blue learners to agree. They're going to need some at least slightly trustworthy third parties. So suppose that all the learners want to terminate as long as no more than one third party has crashed. And red learners want to agree among themselves when a third party is Byzantine. And blue learners want to agree with each other when a third party is Byzantine. So when can red learners agree with blue learners? Well, suppose that they want to agree when a red acceptor is Byzantine and a blue acceptor is Byzantine, but none of the third party acceptors are Byzantine. Well, how many third parties do we actually need? If you use a regular old homogeneous Byzantine Paxos, then we still have some red learners who want to agree in the presence of 5 failures. 5 failures means you'll need 16 homogeneous acceptors, which means 10 third parties at least. And your consensus would look like this. They'd have quorums of any 11 acceptors. But heterogeneous Paxos can save us some resources here. It turns out that we only need 3 third parties. Any 2 red acceptors and any 2 third-party acceptors form a quorum for red learners. And likewise, any 2 blue acceptors and any 2 third-party acceptors form a quorum for blue learners. You can see that if there were a third-party Byzantine failure, red learners could disagree with blue learners. But that's okay, according to the learner graph. So we've implemented this scenario. For our experiments, we use a light client, which wrote transactions and passed them to some proposer machines for the Paxos process. Paxos has the best case latency of 3 messages, or 5 once we include the messages to and from the light client. We put 100 milliseconds of artificial latency on the network connections, and therefore the theoretical best time would be 500 milliseconds. We ran homogeneous Byzantine Paxos, which is pretty easy given that our heterogeneous Paxos reduces to the homogeneous case if we give it homogeneous assumptions. So we used 16 acceptors, and a median latency turned out to be about 555 milliseconds, or 55 milliseconds of overhead processing time. In contrast, the heterogeneous setup using only 9 acceptors had only 37 milliseconds median overhead processing time. Here we've plotted the distribution of latency for appending 1,000 sequential blocks to our little blockchain. The bars are the top 5%, bottom 5%, in median latencies. The reduced time comes chiefly from having to process fewer messages, which means fewer signatures, fewer hashes, and so on. So demanding that this example system use a homogeneous consensus costs an unnecessary extra 7 third-party acceptors, which adds an unnecessary 51% median latency. So that's the kind of consensus you need when you have heterogeneous acceptors, heterogeneous failures, and heterogeneous learners. We built a heterogeneous consensus. We formalized a definition for what it means to have a heterogeneous consensus. We express heterogeneous failure assumptions with a learner graph, and we have a quorum requirement that tells us when consensus is possible. Our consensus, put very briefly, runs 1 Paxos per learner, where 1B messages can include "I've accepted in another Paxos." I'd like to thank the OPODIS committee, as well as my co-authors Xinwen Wang, Robbert Renesse, and Andrew Myers. I am Isaac Sheff, and at this URL you can find links to our paper, this presentation, these slides, and our technical report. Our paper includes a detailed step-by-step description of heterogeneous Paxos, and our technical report includes additional examples of heterogeneous consensus scenarios and additional experiments, as well as proofs of correctness. Thank you.